With the progress of time and the proceedings of the lectures, that has brought to the final stage of the Unit 2 of the course contents, and we will be having the Part C to begin with. As you can notice and observe, we will be coming now to the series solution of the differential equations, spatial functions that we have done earlier, and in this part we will be doing the Legendre polynomials and the Bessel's equations, and then we will switch over to Bessel's function of the first and the second kind. One of the most important, or in other words, now in spatial function begins all those functions where differential equation plays a very vital role, very important role. We have done before this the beta and the gamma function. In that we never had any name of differential equation, but rest all spatial functions, in total about 39 of them, they follow the differential equation. As I have told you, this is the final part of the Unit 2 that has in store many important topics, particularly in spatial functions. We have had discussed some, and the remaining we discuss now. These are the two Legendre and Bessel functions. Though the time and the number of lectures are the constraints, but we will make it convenient for you, more comprehensive, and I believe that it will be understandable by all the viewers. We come with the Legendre equations. As you can see, the equation 1, that is a second order differential equation, as it's given by equation number 1. This is what is called as Legendre's differential equation, n being a positive integer, or in other words, n is a constant. This equation can be written in this fashion also. If you differentiate with respect to x, the whole thing within the curly bracket, then you can have the same equation as given in equation 1. We would like to make the complete solution of this equation number 1, or in other words the equation number 2. Equation 1 can be integrated, that is, it can be solved, because any solution of differential equation is nothing but an integration in series of either ascending or descending powers of x, but for our convenience we will be considering only the descending power of x. That is very important. We will suppose this y is equal to sigma r is equal to 0 to infinity a r subscript x to the power m minus r. Again, m is an integer, but look at this particular thing. This is what we call as the series, and we will be making it a series solution to find the complete solution of, or the general integral, or the complete integral of equation 1. We assume that this is the solution in series for the equation 1 in descending power of x. Descending powers of x means it will go that it will be x cube, x square, x, and finally it is a constant. We differentiate equation 3 and we get dy upon dx. We differentiate again and we get d2y dx square. Differentiation on the right, we believe, will not make any problem for us. We substitute this 4 and 5 in the main equation number 1, which is called as the Legendre differential equation, and after a little bit of adjustment, taking the coefficients of different index of x, we get this equation 6. But this is an identity. There is a difference between equation and identity, we all know. We equate to 0 the coefficients of x to the power m, and it results as equation 7 after all is equated to 0, taking the note that a0 is never equal to 0, and therefore we will be having m is equal to n, and the other value is minus of n plus 1. We proceed further and equate to 0 coefficients of x to the power m minus 1. Once again equation 8 results, where the quantity just above the equation 8 you can see is equated to 0, but since a1 is equal to 0, rest all the things written at the bottom, because the quantity inside the bracket for all values of m, that is given in 7, and so a1 will give you the 0. Now equate to 0 coefficient of x to the power m minus were in the similar fashion, and we get equation 9 that gives us the value of ar in this particular form. Since a1 is equal to 0 in equation 8, the relation 9 will result into A1, A3, A5, all odd constant coefficients are equated to 0. Two cases very important arises, and these two cases are when m is equal to n. This I am referring to the solution that we get m is equal to n and m is equal to minus of n plus 1. The relation 9 or the equation 9 gives us this solution, equation 10, after a little bit of simplification, which is not possible for us to render here or to do all these calculations. This for different values of r is one solution of 1. That means it is the first solution of the Lysender's equation. Second case, referring to the previous equation, when m is equal to minus of n plus 1. Again, we put this value in 9 and using the 3 we obtain this result, another y is equal to this thing. This is the second solution of the equation 1. So, to make a brief note of everything, we say that equation 1, which is called as the Lysender's differential equation, gives two kinds of solution. One that we have obtained earlier as the first solution, and now we have the equation 11, which we call as the second solution of the given equation called as Lysender's. Solution of Lysander equations are called Lysander functions. Make a note of it that Lysander functions are nothing but the two solutions of the Lysender's equation given by equation 1 on the very first part of it that we have discussed. Lysander solution of the first kind is given by equation 10 and is denoted by p and x, n being the subscript. Again, n is a positive integer or a constant. Lysander solution of the second kind, as we were talking about the first and the second kind, one is p and x, the second obviously will be denoted by q and x. N in both the cases are taken as subscript. The nature of the series 10, that means there are two solutions, one is given by 10, the second is given by 11 that we have seen. One you will be denoting by p and x, the second you will be denoting by q and x. Equation 10 shows that it will terminate. By this word terminate or the phrase, we mean it is a polynomial. Terminate and it becomes a polynomial when n is a positive integer. Therefore, we have the heading called as Lysender's polynomial. In a convenient form, the 10 can be written as equation 12. Then the polynomial stands as this equation, equation 13, which terminates with the term involving x if this one is an odd integer and with constant if n is an even integer for both odd and even integers. Before we come to 14th equation, the same thing is repeated. We call p and x is the Lysander polynomial of degree n. Soon we will coming to a very important note, but right now we conclude that out of the two solutions, one is p and x, another we call q and x. This p and x is called as Lysander polynomial. That means the first solution of the Lysender's differential equation given by equation 1 that we started with. The series 11 is not a polynomial. This line is to be underlined, is to be remembered, is to be taken care of. And so the series given by the solution 11 is not a polynomial. The reason given below is we consider this a0 given by the expression for y then will be given by this result, equation 16. We see that q and x is a non-terminating series, n is a constant, that is the number of terms is infinite. Therefore, to conclude these things before we come to the second section of it, after Lysender's function, Lysender's differential equation and Lysander polynomials, the solution of the first equation are two and we call them as Lysander functions represented by p and x and q and x, and then p and x is called Lysander polynomial because it terminates. Q and x is not called as polynomial because it is a non-terminating series. In short, we call this does not terminate, and the reason given here because it is infinite. We come a very brief note about orthogonal function. Numerous books and research papers have been written on orthogonal function. but we have a very brief noting about it. Real functions like f1, f2, f3, so on are said to be orthogonal on the range AB if AB is obviously the range of integration. If this integral is equal to 0 given by 16th equation, and this is valid for m not equal to n. But the same system is called as orthonormal. There is a two different word, we call it orthogonal and orthonormal. If integral a to b fn x whole square dx is equal to 1. So these are the two things. The second, when it is equal to 1 with fn x whole square integrated over a to b with respect to x, we call it orthonormal. Otherwise, if it is not so, then for two integers n and m both greater than 0, range a to b in which the integration is performed, it is equated to 0, and then we call it orthogonal. We come to some properties which are called as orthogonal properties of Legendre polynomials. These are the two properties. We are not going to give any solution, any proof, any deliberation on equation 18 and 19. One is minus 1 to 1. The second integral is also minus 1 to 1. The first integrand is Pnx Pmx, where the two integers are not equal. In 19 also the two integers are not equal, but it is given as Pnx whole square dx. Results are given on the right hand side of 18 and 19. The recurrence formula, basically recurrence is a word used for repetition, or in other words we say that when anything repeats number of times. In mathematics this is also called as iterated method. Also it is called as method of repeated integration, but here we say it's a recurrence formula. Every function has a recurrence formula except beta and gamma, hypergeometric functions as Legendre, Bessel, and then other like Hermite polynomials like Lagore polynomials. Right, for the present text we have this. There are few recurrence relations I have mentioned. One of them is NPN. We have not written x, not necessary. X is a variable known unless otherwise you create some other variable like theta or r or y. But if it is written Pn or Pn minus 1, Pn minus 1 and Pn minus 2 are called as Legendre solution of the Legendre equation of order n minus 2 and n minus 1. We have total 6 recurrence relations given, are made into this list. P dash indicates the prime. In other words, we differentiate the p and we get p dash. In other words, we will be writing dpn over dx will give you p dash. So all these dashes that you see in 5 and 6 recurrence formulae are their differentiation. Fair. Up to this, Legendre is taken care of. The next is Bessel's equation. We have finished the Legendre's equation, Legendre functions, Legendre polynomials, the recurrence relation, everything. We come to the second very important name called as Bessel's equations. Here also we will be finding Bessel's functions, and at this particular time we must be making it very clear that we will be having again two kinds of Bessel function called as of the first kind and of the second kind. We will talk about their notation as we had Pnx and Qnx later, little later. This is again a second order differential equation marked by equation 20, is called Bessel's differential equation, where again n is a positive constant, the same as we had in Legendre's equation in equation number 1. The equation can also be written as the same thing we have also written for Legendre's as well. It is written as this, that is given as equation 21. We talk about now the solution of the Bessel's equation, whether it is 20 or equation number 21. We again start with the series solution of which we talked earlier, which we call as a power series, if you recall. This is equation number 22 that we had, and we had dy upon dx, again differentiating equation 22, we get 23. We are differentiating with respect to x. we make a second differential again and we get 24. The differentiation is very easy. It is all based on d dx of x to the power n form, and you can find very easy to put this equation 22, 23 and 24 in 21 that you have seen, and we simplify a little bit. What we get is this 25. Since 25 again is an identity like what we have in case of Lysender's solution, coefficients of various powers of x must be 0. That is the characteristic of identity. It is not the characteristic of equation. We keep on equating coefficients of various powers of x to 0. To begin with, we have x to the power k minus 2 is equated to 0, and we get this. If you recall, the same thing is appearing here. In that case, Lysender's, I will tell you, we had m is equal to n and m is equal to minus of n plus 1. We have here k is equal to n and k is equal to minus n. Obviously, a0 can't be 0. Then we equate the coefficient of x to the power k minus 1 to 0. We have this, and this results into a1 is equal to 0 because 1 plus k whole square minus n square is never equal to 0 due to the equation 27 we had. Now equate to 0 the coefficients of x, k plus r. We get this ar plus 2, which is almost the same that we had in the Lysender's. We have them as ar. Now, as you see equation 31, all odd constants a1 is equal to a3 is equal to a5 is equal to a7, everything becomes equal to 0. We will be discussing two cases. These two cases are similar to what we have discussed in Lysander solutions or Lysander functions then we defined. The one is when k is equal to n. The second we will be dealing when k is equal to minus n. We will refer to equation 30, and what we now have is this one. If I take k is equal to n, then I will be having ar plus 2 is equal to minus times ar r plus 2 in the denominator into 2n plus r plus 2. That gives us equation 32. Then we put r is equal to 0. You can see here in left hand side as well as in right hand side in numerator and denominator, we have all r present here, and so we take r values of even numbers starting from 0, then 2, then 4, then 6 and then 8. We continue up to the infinite number of terms, and so we get a beautiful or a elegant shaped equation. We numbered it 33. It is y is equal to a0, and inside the bracket you can see that the numerator is ascending x square, then we have x4, then we will be having x6. All are alternate positive negative, and in denominator you can see the first term is 2 square, then we will have 2 4, then we will have 2 to the power 6. In the first denominator we have factorial 1, then we will have factorial 2, naturally we will have factorial 3 in the bracket. It is n plus 1 in the first denominator, we will have n plus 1, n plus 2 as you can see in the second. Obviously in the third term we will have n plus 1, n plus 2 into n plus 3 in the denominator. Likewise, we will be proceeding, and we have a first part of this equation called as y is equal to given in equation number 33. Then we take the case as k is equal to minus n, and we get similar thing. We get ar plus 2 is equal to, note that we do not have any negative to start the right hand side, and so it is ar upon r plus 2 minus 2n in the denominator. Again we put the same thing, r is equal to 0, 2, 4, 6, 8, so on, and we get y is equal to a0 x to the power minus n. If you look into this series, it looks almost the same, x square, then we have x4, in the denominator we have 2 square and then factorial 1, same thing. The only difference is in denominator now we will be having n minus 1 and 2 minus n, alternate positive negative terms. That makes the series more convergent, but right now we are not concerned with the convergence or divergence of the series. So that results into 35. Interesting is that 33 and 35, like Lysender's case, we have two series, both have to start with y is equal to something. One is called the Bessel's solution or Bessel's function of the first kind. We denote it by Gnx and the subscript. We call it order of the Bessel function. The second is called as the second kind, and we denote it by J minus n. X is a variable, minus n is the order of the Bessel functions. So, if I summarize everything, Lysander solution and Bessel solution with two different kinds of equation, but one thing is very common, they both are second order differential equation. The first is Pnx and Qnx are called as two solutions of the Lysander's equations. They are called as the first and second kind Lysander function. Similarly, we have Bessel's function also is obtained from a second order differential equation, where we have Jnx and J minus nx are known as the first and the second solution. In other words, we call Bessel function of the first kind and Bessel function of the second kind. That completes the whole between relations and elegant theories. Very briefly again, not we couldn't be able to make it very elaborated, are the theories of Lysander function and the Bessel functions. This is the time when we summarize everything, though during the course of this lecture I tried to summarize in between, in the gaps, in the place, in the span of the time that we carried over the two names Lysander and Bessel, but at a very pinpoint conclusion is that we have done the most elegant two very fundamental type of special functions which we call as Lysander's and Bessel functions. We have done their solutions. One is called as Lysander's second order differential equation, the other is called as Bessel's second order differential. Then we have started with Lysander's differential equation that I kept telling you during the lecture, and then we have tried to obtain the solution of the Lysander function first, assuming that there is a power series. So, in other words, we can say that is elegant illustration of the use of power series. As you can see, we have substituted y is equal to sigma, we had n is equal to 0 to infinity a n x to the power m minus r. So, r is a positive, n is a positive constant. We differentiated and kept on doing this in both the cases. And at the final, or at the end of the Lysander's solution, we got two beautiful notations. One we denoted by Pnx, the second with Qnx. Pnx was called as the solution of the first kind. We call it Lysander's first function. Qnx, the second solution, we called it Lysander's second solution. But one thing remarkable that we have noted here, Pnx is called Lysander polynomials, but Qnx is not called as Lysander polynomial. Reasons have been given there, and it should be noted that Pnx is a terminating series. In other words, it is a finite. Qnx is an infinite series. In other words, we call it a non-terminating, and therefore Qnx is never a polynomial. Then we switched over to orthogonal polynomials. We gave two relations, and then we said about what about the orthonormal. In orthogonal polynomials, we have n and m as integers. Soon we switched over to Bessel's function, followed the same type of solutions starting from power series. We got two solutions. One is denoted by Gnx. We call the first kind of solution or first function of the Bessel's equation, and the second solution is called as the second solution of the Bessel's equation. One is denoted by Jnx, n is the order. The other is denoted by J minus nx, minus n again is the order. So, likewise, we try to make you understand, or we have understood, what is the application of the power series by illustrating these two functions, and I would like to draw an underline to it. The line is that now onwards, wherever you will be studying the special functions, all will be generated by, or they will be having a solution generated by the power series. However, thank you very much for your attention, and we hope that you will be able to apply or find some applications of Legendre and Bessel functions which are in abundance. Thank you.